All right, welcome everyone. Welcome to our weekly machine learning workshop. Today we're going to kind of put a little bit of a bow on some of our discussion of linear regression, which we've been talking about for like the last month or so. And today we're going to learn a couple of advanced-ish techniques that are going to take, a vanilla linear regression and make it a good predictive model. And so before we get started, today's discussion will be a little bit different because usually I have two notebooks to give to you, one that's blank that we kind of code in as we follow along together, and one that has the completed version of the code. Today I'm just going to give you the completed version of the code, and the reason for that is that there is a lot of code in today's notebook, and if we were to type it all out together, it would take a really long time. And so all of the code that we're going to write today is already written. We may write a little bit, we may tweak what's here. But the reason for this is that we're going to learn the why and the behind the scenes of why to use regularization, what regularization does, really wrap our heads around the concepts of over and under fitting, the bias variance trade-off, and like a bunch of kind of theoretical stuff. And then the code to actually implement what we're doing is like somewhere from 2 to 5 lines of code. Right, so there's a lot of code in this notebook that is really demonstration and hopefully really showing why we're going to be doing what we're doing with our linear regression model, why we're going to do regularization, what effects is it going to have, all those sorts of things. But when it comes to you on the day-to-day implementing these tools, you're really just going to switch out your linear regression model for one of these. You might do a little bit of extra hyperparameter tuning, which we'll talk about, and we're also going to talk about the importance of log normalization of skewed variables. Our sales price variable is skewed, and we also have some X variables that are skewed. And so between using a regularization technique or a regularized linear regression model and log normalizing our skewed variables, those two things are going to cause our predictions to get lots better. And we'll go from being like an average model on the Kaggle leaderboard to being in the top 10%, 8%, something like that, 92nd percentile with just these two things. But there's kind of a lot of background we need to establish. So that being said, let me share with you our one notebook for today, a little bit different than usual. I'll paste the link in the chat. You can also find it in the video description. There we go. And we're going to get going today. You notice we're importing all kinds of stuff. Not much of this is new. What's new is these three models. These are regularized linear regression models. And then we are importing this scale variable, which we very briefly scaled our data at the end of our previous discussion. We'll talk about that a little bit more today. But everything else here we've used in the past. Okay. And what I want to talk about, and the reason why we need to use regularization with our linear regression model is due to something called overfitting, right? A model is overfit when it does really good on the training data, has a really low error metric, mean absolute error, mean squared error, root mean squared error, whatever your metric is. It's low on the training data, but high or higher on the test data. Now, that is always going to be true to some degree with really any good model. Any good model is going to do a little bit worse on the test data than it is on the training data. But the bigger that gap becomes, the bigger the difference is in the model's ability to generalize, which remember is our ultimate goal. The bigger that difference gets, the more we say that our model is overfit. And the real culprit of this overfitting is the model fitting to noise in the data rather than the general trend, right? Now, what is noise, right? We use this word a lot, but noise, as it says here, is classified as a naturally occurring random or irrelevant variation in the data that doesn't represent any true underlying patterns or relationships, right? So it's variation in the data, but we don't have any X variables that can speak to it. It's just there. And no matter how good of a model we make, no matter how good of feature engineering we do, there's going to be some amount of unexplained variation in the data. And so that's what we call noise, right? With linear regression models, the greater the number of features, x variables, that are included in the model, the more the model has a potential to overfit. Also, some of the types of features that we add to the model have a greater likelihood to overfit. So in this graph you're seeing here, this left graph is an example of what we call an underfit model, meaning that the model's complexity is not complex enough for the phenomenon that we're seeing, right? And this is what we might have if we were doing simple linear regression, right? We just fit the best straight line of best fit we can to this data, when really this data has some curvature to it. It has some nonlinear relationships that are not being captured by our simple linear model, right? And so this is a model that we would call underfit. And you can tell that a model is underfit if the model does worse on the training data than it does on the test data, or really close, maybe slightly better on the test data than it does on the training data, right? That could be an indicator that maybe we need to make this model a little more complex. Maybe it doesn't have enough flexibility to fit to the patterns that exist in the data. On the other hand, a model that is too flexible starts fitting to individual data points, that variation, that noise, rather than this, what we call a good or robust fit here in the middle, where the model is capturing the general pattern to the data, but is more or less ignoring the noise, right? So that's kind of our Goldilocks zone. And this model in the middle is not only going to make good predictions, but it's also going to generalize to unseen data better than any of the underfit or overfit models. Now, what they've done to make this model really bad is they have used what's called a polynomial fit. With linear regression, you don't have to just throw in your x variables as they come. You can do feature engineering, which means you can combine and recombine your x variables in lots of different ways. And one common way is to generate polynomial terms, right? Take a column and then square every value in that column, create an x squared variable, or cube it, or raise it to the fourth power or fifth power, or whatever you want, right? We usually stick to the second or third power. In some extreme cases, there may be justification for using a higher polynomial, but these polynomials, because they're already curved, right, they tend to allow our model to twist and turn a lot more than it would normally. And in fact, if we use polynomial features where we have more polynomial x feature terms than we have data points in the model, we will actually achieve a perfect fit. And this is part of what this is showing here, is that the model is allowed to twist and turn so much that it goes exactly through every single data point. But it's a pretty wild model. It's a pretty noisy model. And well, I want to try and do that together with you on purpose. Let's see if we can purposely make a model really overfit, so that I can show you in the context of our data set how that gap between train and test widens. Okay, and I've already got a lot of this data prepared for us here. One of the things that's going to help me overfit to the model is if I have a smaller amount of data. The more data I have, the harder it is for to fit to individual data points. So I'm going to make my train and test data sets smaller here, which is kind of slightly cheating in this demonstration. But we're going to have just 100 data points in train and 100 data points in test. Okay, we still have our original 81 columns, and start off with a simple linear model, right? And what I want you to watch here, I want you to watch our coefficients as well, right? This is the simple linear model we've used weeks ago with $112.8 per square foot sale price slope here, right? For every increase in the square footage of 1 square foot, the home's value goes up by $112. That's what this coefficient's telling us, right? And one thing I also want to take a moment here to acknowledge is that when we use linear regression, different practitioners, different users of this model kind of have different priorities when they use it. So there's an application of linear regression that we call statistical inference. And the whole goal of inferential modeling is to really nail down the values of these coefficients, to really, as precisely as we can, estimate the relationship between square footage and home price. And this is the field of econometrics, and most academic research that employs linear regression, that is their goal, is to nail down these coefficients. Our goal as machine learning engineers, data scientists, is quite different than that. Our goal is to make the most accurate predictions possible and to have our models' predictions generalize well to unseen data. It is like a nice to have, in most cases, a secondary benefit to be able to interpret these coefficients and for them to have meaning. What you're going to see today is that as I throw lots and lots of columns into this linear regression model, some of these coefficients, they're going to go a little bit crazy. And that's the whole reason why we need to use what we call regularization. Regularization is a tool that's going to help us bring these wonky coefficients back down to reality, and is in fact going to improve our model's predictions by quite a lot. Right? So overfitting is one of the reasons why we're going to need regularization, but also kind of the wonkiness of these coefficients is the bigger reason, and there's also a very important second reason for why the coefficients go wonky, called multicollinearity, which we're gonna get to later. But that tangent aside, let's come back to demonstrating an overfit model. Right? So we're gonna do a different. Okay, so check out our root mean squared error here. By the way, I'm going to use root mean squared error today because once we transform our y variable to be not just sale price, but to be the logarithm of sale price, that combined with using root mean squared error as our error metric will then match the Kaggle leaderboard. And we'll be able to see scores in our notebook and go, oh, that score's better than what I have on the Kaggle leaderboard. I might have a model that's better than the one I used to submit with last time. So we're going to take a little change of pace from using mean absolute error, as we have in past weeks, to using root mean squared error today. So which is just mean squared error, and then you take the square root of it. Okay, just so you know. R squared is a measure of goodness of fit in linear regression models. The thing about R squared is as you add x variables, R squared will always go up. Right? It's a value between 0 and 1. 0 is a terrible fit, and 1 is a perfect fit. The model is going exactly through all the data points. So you're going to see as we add more x variables, as we get more and more overfit, the R squared is going to go up. There is something called adjusted R squared, which kind of tries to account for the fact that, well, the fact that R squared goes up every single time makes it not that useful of a metric, right? If I add some total garbage x variable, R squared is still going to go up a little bit. Right? So typically with R squared, the higher the better. But if you get to an R squared like above 0.85 or 0.89, you should start to get suspicious that it's too good. An R squared of 0.5 is like not very great either, right? So it's kind of a fickle metric. And I'm not really going to speak more to it right now. A traditional linear regression course would talk a lot about R squared and F-tests and a whole bunch of stuff that we just don't care about as much in the context of predictive modeling with linear regression, as opposed to inferential modeling with linear regression, which is what most statistics courses, especially university statistics courses, are training you up for, because they're trying to get you prepared for academia, which is one of the reasons why I feel like it's important to have this live stream here with you today, right? Because we're going to be tackling this and viewing this from a pretty different lens than your traditional educational institution might look at it from. Okay, anyway, so what were we doing here? This is our first root mean squared error, when we just have one x variable, greater living area. And you can see that we're kind of in the ballpark with our test root mean squared error, right? We're not generalizing super well to new data, but we're about, what, $4,500 off between these two. Okay. The more overfit we get, the wider that gap is going to get. Okay. Actually, this root mean squared error is not good because we just have one x variable. So as we add more x variables, we'll see both of these go down, but the training root mean squared error is going to go down faster than the test, because our model's ability to generalize is going to get worse. Our model's going to think it's doing better on the training data when really it's just fitting to noise in the training data. noise that's not helping it make better predictions with the test data. Okay, so as a reminder, here's our line of best fit, and we'll come back to this in a minute. You've seen this line of best fit 10 times at this point. Let's go again, but let's choose a different X variable, overall quality. Overall quality is a much stronger predictor, right? Our root mean squared error is much better. Our R squared is also much improved. And our root mean squared error, like on the test, is not as good, right? So our training root mean squared error has gone down from 48,000 to 37,000. It's a drop of $10,000, $11,000 per home. It's a big drop. But the test root mean squared error has only gone down by 2,000, right? So that gap is widening. Okay, now let's see. Here is the scatter plot for overall quality, and we'll talk more about this scatter plot here in a minute. So we'll come back to that. Okay, now let's do a slightly more complex model, a multiple linear regression model. Let's use both of these X variables. Okay. And what I want to point out, now that we've fit these three models, is take a look at the coefficients. Okay, I'll start at the top. We had $112 per square foot and $40,000 per level of quality. So there was 10 quality levels. As you went from 3 to 4 and 4 to 5, 5 to 6, that increased the value of your home on average of 40-something thousand dollars. What was it again? Well, yeah, $40,352. That is the average increase of going up one quality level in the quality rating. Okay, but once we put them together, what happens? Well, now this price per square foot is $44 per square foot, and the increase in price of going up one level of quality is only $31,000. Okay, now that we've put those two X variables together in the same regression, that same variation in price that was previously being explained by just one or the other of these two now has to be shared between these two X variables. So both of them are lower. Both of them are lower because they're splitting the same variation in sale price between the two of them, right? So when we have just one X variable, we say that this X variable has soaked up the effects or the variation in Y due to the lack of other X variables. So like this coefficient is almost certainly overstated because there's a lot of other things about homes that we're not accounting for right now, right? And so the only thing we have to go on is quality level, and so quality level gets all the credit for the change in home price, right? So as we add more X variables, generally these are going to go down. These coefficients are going to go down, generally speaking, okay? We're going to see in a few minutes some instances where some of these skyrocket and go into the hundreds of thousands, and that's bad. That's why we need regularization, okay? So just keep an eye on this. Keep an eye on this. All right, let's see. Are we overfitting any less? So here's our training root mean squared error. What about our test root mean squared error? We're doing a lot better on the test root mean squared error. It's just dropped by quite a lot. So this model is generalizing much better than either of the other two. Makes sense. The quality or the value of a house is kind of a mixture of its size versus its quality. And we're capturing kind of quantity and quality with these two variables. They're both strongly correlated with Y. This is what we like to see. We like to see that test metric go down. But we're still doing a lot worse on the test metric than we are on the training metric. We're still overfit somewhat, kind of a lot. Okay. So what happens to our linear regression model, right? This is when we have just one X variable. This is when we have one X variable, a different X variable. What happens as I add more and more and more X variables? Well, what if I have two X variables? Well, from a spatial perspective, my linear regression kind of becomes this 3D scatter plot. Sale price is the vertical space here. And my linear regression, instead of being just a line, it's now a plane plane fitted to this data. And if I were to add a third x variable, then I would get a hyperplane, a plane that exists in 4 dimensions, which I can't graph for you, unfortunately. Okay, but I want to show you something interesting, is that as I add more and more x variables, right, this imaginary plane is still slicing through those data points as best it can across however many dimensions of data we throw at it. But if I look at it edge on, okay, so this is overall quality on the x-axis and sale price on the y-axis. This graph, let's see if I can make it a little more visible. This graph is the same as this graph. So looking at that plane edge on would be the same as the simple linear regression model. Same as if I looked at it this way. That is the line of best fit between sale price and living area, square footage. Let's see if I can scroll up. So kind of look at this shape, see where the dots are above and below, line cutting through. It's not going to be exactly right, but it's going to be in the ballpark of this. This is just kind of stretched out, smaller dots, etc. Okay. So while as I add more x variables, I can't show you this crazy n-dimensional hyperplane through our data points. I can, however, show you a cross section of the line of best fit of each of our dependent variables, each of our x variables, each of our features on against the target. Okay, so with that in mind, we're going to do something a little bit that we've never done before. We're going to create our very first polynomial feature. We're going to take overall quality and we're going to square it. Okay, and what that's going to do is it's going to allow a quadratic curve to be fit to this data. Okay, now as you take a look at this, can you see that a curve might fit this slightly better than this line would, right? If you follow my cursor kind of somewhere through here and then slightly below and then curving upwards, right? We've got these points above the line on the right and below the line on the left, and we're kind of, a curve might be a hair better of a fit to this data in particular than a straight line would be. And this graph may not have the perfect shape to show us that. I could maybe change if I change the figure size and squished it horizontally, it might be a little bit clearer. Let's see if I can do that real fast. If I just use a regular matplotlib graph. No, I gotta say train and train. X and Y must be the same size. Oh, it thinks that this is X. So with Seaborn, you pass the data frame first. And let's add an alpha, which is the transparency value of 0.3. Maybe just 0.5. Okay, and I don't really know if you can see it any better here, but there's a slight curviness to it. Okay, that's something we could test numerically as well, but oftentimes just eyeballing will help as well. And you don't have to get it exactly right. If you make a squared term and you add it into your linear regression and your predictions get worse, well, take it back out again. You can always run that experiment. Okay, so what I'm saying is I'm not doing this willy-nilly. I think there's some justification for creating a squared overall quality term. Okay, and our linear regression equation just gets this squared term added on. This x input gets squared before it gets multiplied by the coefficient. All right, so I've got overall quality plus overall quality squared now. And I've got 3 different coefficients because I've got 3 x variables. And our root mean squared error has indeed gone down. And our goodness of fit measure has gone up. Let's see what happens to our test root mean squared error. So we got 42.5, whereas before we had 44.2, right? So our model is generalizing better to unseen data as well, right? So the adding of this polynomial feature is capturing something about the model that's not just noise, right? It's capturing something about the shape that maybe overall quality on its own was not fully capturing, right? So our model's getting better. Our model is getting better, but we still see some overfitting of about $11,000. Okay. Well, what if I went crazy? What if I added? Oh, here's by the way, here are the cross sections I was telling you about. Greater living area against sale price, overall quality against sale price. And this is overall quality squared. Now, instead of having a curved line, we have curved the data or straightened the data, right? So you can see that even though these two graphs look the same, they are in fact a little bit different. Look at the gap between this third point here and the line. It's almost right on the line here. So you'll notice that points on either extremes are a little bit closer to the line. This curved line is a slightly better fit than this one. You can do it either way. You can curve the line to your curved data, or you can straighten. You can take out the curve to your curved data, but yeah, it's really the same thing. I don't know if that made a whole bunch of sense, but this is the cross section of my four-dimensional hyperplane, right? Viewing it on all three of its sides. Okay. So long story short is that you can still look at graphs of x variables against y variables. You can still look at the line of best fit even if you have lots of x variables like we're doing here. Okay. Well, this is me going crazy. I'm going to make a third degree and a fourth degree and a fifth degree, sixth, seventh, eighth, ninth, 10th degree polynomial of overall quality. And I'm going to throw them all in. Okay. And that's going to allow my linear regression to twist and turn. And each of these is going to have its own slope coefficient, determining its shape. And because I'm doing this a little bit willy-nilly, and this isn't even like all that terrible, my model's going to start to fit to some of the noise in the data more than the overall patterns of the data. Okay, I'm going to do this to both train and test because I still want to see what my test root mean squared error is to see if that overfitting is getting worse. So I've got a lot of coefficients, and notice that a lot of these coefficients are, some are big, some are small. A small coefficient means that x variable does not have a very strong relationship with the y variable, right? So in fact, there's something called an F test that tests whether or not these coefficient values are non-zero. And if we wanted to be really thorough, we would maybe go through all of our columns of our model, and anyone that didn't pass the F test, we would take it out and see what happened to our predictions. We're not going to do that today. We're just going to leave our quote-unquote kitchen sink model and leave all of our hundreds of columns that we end up with after one hot encoding. We're going to leave those in, and you're going to see that our predictions are still going to be pretty good. Because remember, at the end of the day, we as predictive modelers don't care as much about the coefficients as an inferential statistical modeler would be. Someone who is more interested in the explanatory power of these coefficients. That's not our top priority. Okay. So here's our training root mean squared error. Has it gone down? It's about 29.3. Before we were at 31.4. Okay, so it has gone down. What about our test root mean squared error? 41.9 versus 42.5. So it has gone down. Our test root mean squared error has gone down a little bit. It's gone down by about 600. But our training root mean squared error has gone down by 2,500. So our training root mean squared error has gone down by 4 times as much as our test root mean squared error. That means the gap between our model's performance on training and our model's performance on test is widening. That overfitting is getting worse and worse and worse, right? So as you are training these models, look at your training error, look at your test error, and if they're really far apart, this is actually pretty far apart, then you might be worried about overfitting, right? So just trying to help you gain the tools for where you can naturally spot, uh-oh, maybe my model's overfitting. Uh-oh, maybe my model is underfitting, just by kind of comparing the training and test metrics. Okay, so as we add more and more and more columns, my model's going to be allowed to twist and turn more, and it's going to be a more overfit. So more X variables is going to lead to a greater potential for overfitting. And this leads us to kind of a generalized version of what we've been talking about here, called the bias variance trade-off. The bias variance trade-off is an important general topic. It's something you might even get asked about in an interview or something like that, right? And what is this bias and what is this variance, right? Bias is error in our model's predictions because our model is too simple relative to the complexities and nuance of the real world, right? So a model that is very biased might be underfit, right? It is the difference between the average prediction of our model and the correct value. A model with high bias, didn't mean to double click on that. A model with high bias oversimplifies the model and does poorly on both the training and the test data. So a highly biased model is missed the boat and is likely underfit. Okay. Variance is the opposite of that. Variance is my model's ability to be flexible, to twist and turn, right? The model's sensitivity to small fluctuations in the data. A model with high variance pays too much attention to the training data. It performs very well on the training data, but scores poorly, or does poorly on the test data. So delete one of those words in your mind. Okay? So this is kind of the trade-off between underfit versus being overfit. And we don't want either. We want to be kind of somewhere in the middle, right? So a low bias, high variance model, it would really capture all the complex patterns and nonlinearities in the data, but it's going to fit to noise and it's going to be overfit. We don't want that. The opposite, a high bias, low variance model, is a model that is too simple, too rigid. This is like our simple linear regression model. It underfits the data. It potentially misses important complex patterns. The goal is to have a balanced model that has low-ish variance and low-ish bias. We don't want an extreme in either one of these. That's why there's this push and pull, this trade-off, right? Because of the trade-off, it is impossible to be perfect in both of these ways. The model needs to capture important patterns in the data and generalize well to new data. Okay? Very slight tangent. If I had to pick the two, I would pick a high variance model. Because in the real world, oh no. In the real world, our data is pretty nonlinear. Has got a lot of twists and turns and variations and nuance to it, right? Something like this, right? If I was trying to classify this data, which is what's going on here, and this simulator allows me to generate a neural network, okay? And what I'm going to do is I'm just going to give it, notice these two are, this is the regular X and Y position of these data points. This is the squared, X squared and Y squared. Sorry, the X1 squared and X2 squared. So these are our polynomial features. This is what we call an interaction term. This is the sine of X1 and the sine of X2. Just going to give it a whole bunch of input data. But everything after these two is just features that have been generated from the first two. And I'm going to load this up in neurons, right? I'm going to make this model really complex, right? Remember that a bias model is often not complex enough. So the more complex I make this model, the higher variance it's going to be. Okay, and I'm going to kind of cheat here. And we should see the predictions forming over here. The model's going to try and fit to nonlinearities in the data. And what I'm really getting at here is that the more parameters there are to a model, the greater its ability to fit to nonlinearities in the data. But in particular, neural networks, whole category of model, which we haven't really talked about yet, but which the tool we're using here is allowing us to play with, they are high variance models. They're very good at fitting nonlinearities in the data. In fact, too good at fitting to nonlinearities in the data. So neural networks have a very strong tendency to overfit. Let's make this a little bit crazier. Let's start over. What else can I do to make this better? There it goes. It's learning even more about the data. Okay. And this graph over here is our test loss and our training loss. Like this bottom line is how well it's doing on the training data. The top line is how well it's doing on the test data. The gap between those two tells us about overfitting. The more data we give our model, the longer it trains, etc., and the more overfitting happens. So that gap is not what we want. Okay. So we'll get more into this later, but like one of the strengths of neural networks is they're high variance out of the box naturally, right? They're very sensitive to small fluctuations in the training data, and that's kind of their superpower, as they can fit to things that other models would assume to be noise. It will discover to not be noise. It'll figure out how to get meaning from some of those fluctuations that other models would miss. And because of that, it has a strong tendency to overfit. So neural networks really need regularization, which is what today's lesson is all about, right? So another way we can kind of visualize bias and variance, right? A model that is biased just misses the mark. So both of these targets, the model's predictions are these bullet points shooting at this target. Biased is just off center. You're not centered on the truth. Okay. Being high variance, these two models, predictions are high variance. They're spread out. They're not concentrated, right? We would like to have something that is low bias and low variance, centered on the truth, and concentrated, right? The worst scenario is something that is both high bias and high variance, but there's both problems with the mixtures of the two either. All right, so this is another picture of it. Another way to think about it is this image, which I'm going to try and make a little bit bigger here. Okay, and the y variable is our error, right? We want less error. We want to get as low on this graph as possible. And the more complex our model gets along the x-axis, then the less bias it is, but the greater the potential for variance, right? So we want a model that is medium complexity, some optimal complexity where it's capturing the patterns in the data, but it's not overfitting to noise, right? Some model that is in this Goldilocks zone, this sweet spot of truest performance. Not too simple where it's underfitting, but not so complex that it's overfitting, okay? Want to avoid both of those zones, right? Okay, so that is the bias variance trade-off. A kind of an antonym for bias is accuracy. A model that is biased is not accurate, and a model that has high variance means it's really sensitive. It fluctuates a lot. It tends to fit to nonlinearities in the data. Okay, so those are all different words for that. And this is our constant battle in any kind of model fitting, is to find this sweet spot, to find the model that is going to perform well without overfitting, because we want it to perform well, but we still want it to generalize to well to unseen data. Okay, so that's all we're going to talk about, the bias variance trade-off today, but this is what we've seen. As we've added those X features, added those polynomial features, we've seen an example of the bias variance trade-off. We've seen an increasing variance due to those wiggly polynomial features, and less bias as our model gets less simple, gets more complex. Okay. We're going to see this even more. Another big factor that can increase our model's complexity is something called multicollinearity. And this is an issue that is somewhat unique to linear regression models. Multicollinearity occurs when we have X variables that are highly correlated with each other. And it can cause our coefficients to go wonky. Wonky means really extreme. They can either get really big, far away from 0, or really low, really far away from 0 in the negative direction. But they're really extreme. The coefficients get giant, either in the positive or negative direction. They get far away from 0. There's another problem called perfect multicollinearity, which would be a problem if we were kind of hand rolling our own linear regression, calculating it by hand. An x variable is perfectly multicollinear if it has a perfect linear relationship with another variable. If it has a correlation of 1 or -1. And this usually happens by accident when you are doing some feature engineering, when you're making new x variables that you think will better demonstrate the signal in the model, right? So one example is if I change the units of one column and I add a new column. So here's an example. I'm reloading the data set fresh here. We're going to work with, instead of the 100 data points, we're going to work with all of it now. Okay, and I've got pool area in feet squared. Say I wanted to make a new column that was pool area in meters squared. Well, the unit conversion from square feet to square meters is a constant factor of 10.7639, right? A meter is 10.7639 square feet. Okay, and if I do this and I leave both of these columns in my data set, I think they're all here towards the end, right? Pool area M is the column I just made, and pool area here is the first column, right? They're different by a constant factor. If I plot these against each other, oh, that's not what I wanted to show. Let's clear this. Let's see, plt.scatter. Yeah. Plot these two against each other. They're going to be exactly on a line. So there's not a lot of pools in Ames, Iowa, but the pools that do exist, right? These two features are perfectly collinear. And in a lot of models, this would actually cause linear regression to break. Some specifications of linear regression, the math gets some weird divide by 0 error in the middle of its calculation. The determinant of the variance-covariance matrix is 0 or something like that. If that doesn't make any sense to you, don't worry about it. Most linear regression models will notice perfect multicollinearity naturally, and they will automatically drop one or the other of these columns. In fact, this is what scikit-learn does. So if we accidentally generate perfectly multicollinear columns, then this just gets left out for us. I want you to think, what would happen if I were to binary encode a yes/no variable? Okay, whether or not someone likes dogs. We've got a bunch of yeses and nos. If I were to one-hot encode this, I would get 2 new columns, and I would get likes dogs yes and likes dogs no. Right? And I would get 1s where I have likes dogs yes, and 0s where I don't like dogs. And then this column would be the opposite. Okay. So this is a one-hot encoded binary variable. Okay. So we had 2 classes. Those classes each got their own columns. Okay. These 2 columns are actually also perfectly multicollinear. This is something called the dummy variable trap. And it's when you accidentally generate too many dummy variables, one-hot encoded variables for binary variables. Okay. And in fact, this will happen with any one-hot encoded variable. Say I had 7 categories. One of those categories will always be viewed as redundant, one of the 7. And so linear regression will automatically drop one of the categories of any given one-hot encoded variable because the set of all of them together is a little bit redundant. Let me show you what I mean, right? Does the likes dog no column give us any new information that the likes dog's yes column doesn't already give us? No, they're just opposites of each other. There's no new information in this column that was not already captured by this column, right? And so there is no point to one hot encode a binary variable. It's already as signal rich as it could ever be, okay? So no point in doing this. What if we had, I know we've used this example in the past, what if we had a categorical variable that had 3 categories? Okay, eye color, and we're going to one hot encode this to eye color green, blue, and brown. Okay, well, let's one hot encode again. So eye color green, the greens get 1s, everywhere else gets 0s. Now blues get 1s in the blue column, everywhere else gets 0s. Okay. Now if I delete the original column, can we create the third column just from the information that's already here? Well, yeah, I can. I know if it's not green and it's not blue, so if I have 0s in both of these, then it must be brown. Is that right? Let's put the other column back. Brown, brown, brown. 1, 1, 1. Okay, so whenever I one hot encode, I'm actually accidentally creating some perfect multicollinearity. That one of these columns could be deleted and my model wouldn't lose any information. Same with binary. But once you have 2 columns and you delete one, you're just back to the original column. You've just categorically encoded it. Okay. So what I'm saying is perfect perfect multicollinearity happens on accident all the time. Most linear regression models will account for this automatically for us, and they'll automatically drop one of these categorical columns that is not needed because its information is already captured by the other columns, by these other dummy variables, these other binary variables, synonyms for each other. Okay, that is different from just regular multicollinearity. So perfect multicollinearity means there's a perfect linear relationship, but even just a strong linear relationship can be a problem. Okay, and that's what we're seeing in our data set, is we have some x variables that have strong linear relationships with each other. Not perfect. In fact, I don't think we have any perfect multicollinearity before we one hot encode in our data set, but we have some strong correlations. Right? So here's our correlation heat map that we've seen in the past. This correlation heat map is actually lying to us a little bit. It goes up to 1 because the main diagonal has correlations of 1. Any variable compared to itself has a correlation of 1. But in blue, it only goes down to 0.4. So this really dark box, you think, oh, that must be close to a -1 negative correlation. It's actually not. It's actually close to -0.4. So if I give it this Vmin and Vmax parameter, that will force dark blue to be -1 instead of being -0.4. So this is a little more accurate representation of our correlations. Okay. So now you can see that most things in this data set are positively correlated, including positively correlated with sale price. It's whenever we have negative correlations, they're fairly weak. Okay. And this just speaks to the fact that when we measure things about homes, we tend to measure things that we think are good qualities. And in economics, we call this the hedonic housing model. you do not need to know that term, but it's basically the idea that a home's price, a home's value, can be quantified as the sum of all of its characteristics. Simple enough. Most statistical models assume that. But that, you know, having a basement is a good thing, and having a kitchen above ground is generally a good thing, and having a garage, and a big garage, is generally a good thing. But the more house you have, the more value, right? The more of something you have. And there's a few instances where that's not true. People seem to really not like enclosed porches. And enclosed porches are associated with the age of the home. And they also seem to not like unfinished basements. Okay. But you'll notice that most of the correlations are around 0, or they're positive with our data set. Negative correlations are a little bit rare. So the year the garage was built tends to be correlated with whether or not there's an enclosed porch, which is also correlated with just the year that it's built. Older homes tend to not have garages, but they tend to have enclosed porches. And so homes with enclosed porches are valued as less, maybe because people don't like the porches, but maybe just because those homes are older, and an enclosed porch is a marker of an older home. So that's what some of the blue lines are showing us. Okay, so what am I getting at here? Is that there are some places here where we have strong correlations that may cause issues with multicollinearity. Garage area and the number of cars that can fit in a garage makes sense. You need a certain amount of square footage to fit a car in the garage. Let's see, year built and the year the garage was built. The garage is usually built the year the home is built, so those two things are highly correlated. Right? We have some high correlations existing in this data set that may cause our coefficients to go a little bit crazy. Okay? So let me show you here. Oh, this is the same one. I would just, I'm going to actually delete this. We've already talked about this. The only difference here is that this heat map also includes the variable I generated, or does it? It should include pool area M, and we should see a perfectly, yeah, so dark red here, pool area is perfectly correlated with pool area M. That's some really bad perfect multicollinearity. In fact, it's so bad the model's probably going to catch that for us because its correlation is exactly 1. But we have some other high-ish correlations. This is the highest negative correlation. It's around -1/2, which is actually not that high. But the positive correlations are much bigger. Garage area and the number of cars, the number of rooms above ground and the square footage above ground. What do you know, right? And in fact, we could take a lot of these variables and we could combine them. We could combine a lot of the square footage areas maybe into just like one square footage variable. We could combine the number of basements, number of baths, number of full baths, half baths into just like a number of rooms variable, or number of full baths and half baths. We could just say 3.5 if there's 3.5 baths, something like that. Same with like age of the property. Right? There tends to not be a whole bunch of more information in knowing how old the garage is versus how old the home in general is. And some of these other amenities could also be maybe combined in some ways. You notice that some of these like not high priority amenities don't have very strong correlations in general with our Y variable. Right? Whether or not it has a screen porch or a pool or the area of the pool or some miscellaneous value, right? Like just doesn't seem to be moving the needle very much. And so we may not be punished a whole lot by just leaving these out of our regression in the first place. But for now we're going to leave them in just because why not? Okay, so yeah, here's garage area and garage cars. Pretty linear relationship here. Not perfectly linear, but strongly linear relationship. Okay, so I'm going to reload the data set here because I want to get rid of that perfectly multicollinear variable that I made. So let's check, make sure it's gone. Yeah, it's not here anymore. So I don't tend to do this when I'm working on my own. I don't reload the data set 5 different times in the notebook. I'm just doing it here with you when I want to prove to you, hey, we're having a clean start here. So don't think because I'm doing this that like that's a best practice. It's mostly just for demonstration purposes. Okay. Last week we talked about how there's a challenge of treating our test data in the same way we treat our training data, particularly when it comes to one-hot encoding, because one-hot encoding needs to see the presence of a categorical variable to know to make that column. And we used a scikit-learn pipeline to make sure we were treating our test data the same way we were treating our training data. I'm going to show you a quick and dirty similar way to do that today, right? Where basically I'm going to squish my training and test data sets together into one big data frame. I'm going to force my MS subclass column to be a string because even though it's a numeric value, it's really categorical. And that's going to allow this to also be one-hot encoded. And now I will be able to one-hot encode everything all at once and make sure I get exactly the same columns in both train and test. Right? So I'm putting them together. I'm one-hot encoding. And then I'm going to immediately take them back apart, split them back into train and test. And this is one way I can make sure I'm doing this same one-hot encoding treatment to both train and test. So I put them together, one-hot encode them. Now I'm taking them back apart. Okay. And then we're going to do what we've always done. We're going to fill the null values with the mean if it's numeric, the mode if it's an object column. Okay. And now I'm going to do a linear regression. And by the way, I have like a bajillion columns now. Let me show you. Print, just xtrain.shape. 302 columns. After all the one-hot encoding, each of the different categories got its own column. That's a lot of x variables. And I'm going to throw these all into our linear regression. Okay. So you'll notice I have 302 coefficients, 302 slope values, and some of these have multicollinearity. And also some of these just due to the quantity of variables is going to tend to overfit a little bit. Okay? So if I plot these coefficients, whoa, one of my coefficients has a value of negative 500,000. It means if that x variable is present, drop the home's value by 500K. The average price of a home here is like 198,000. So that is a wonky coefficient. This one here drops the value by 400K. This one drops the value by 200K. All right, so this is like a quick and dirty way to show you that some of these coefficients are pretty extreme. In this ballpark, these coefficients are increasing the value of a home by 50 to 100,000. Those are big swings in the sale price. Okay, this is maybe not the most beautiful plot in the world, but it's showing that my model's coefficients are going wonky. My model is overfitting to noise in the data a little bit. Okay, and this is actually a big source of my model's not so great predictions. Okay, and so this is me really just giving all the justification for why we're going to use this new tool called regularization. Regularization is going to combat multicollinearity. It's going to combat overfitting, and it's going to give us, at the end of the day, a better model, a model that makes better predictions on our data. So let's see. Oh, I'm going to make another graph here. I'm putting all of these coefficients into a data frame so that I can plot them in a bar chart. So we're going to look at the 10 biggest and the 10 smallest, or 10 most extreme in both the positive and negative direction coefficients here in this bar graph. Okay, if the roof has a material that is made out of clay or tile, that home's sale price goes down by 550,000, 540,000. If it has a pool quality of fair, then it drops by 400,000. Like this doesn't make sense. These coefficients have gone wonky, right? They're too extreme, and they're extreme because first off, these are maybe rare categories, and the rareness of those categories is causing some overfitting, but also there's maybe some multicollinearity going on as well. The roof material membrane, I think that's what that is. If the roof material is made of membrane versus metal, that really increases the value of a home, like an unreasonable amount. Right? These coefficients are unreasonable. and they're throwing off our predictions. They're overfitting. Notice that these are some of mostly weird categorical columns. They're probably somewhat rare categories got really taken for a ride by our model's fit. Okay, so here's our tool. Here's the medicine. Something called regularization, right? We talked about how our model twists and turns, particularly with polynomial features or with lots of x features, allows our model all these twists and turns. And these extreme positive slopes or extreme negative slopes can be thought of as our extreme coefficients, allowing it to twist and turn in all these crazy directions. Well, we want to take those coefficients and make them smaller. As I take these extreme coefficients and bring them back down to size, bring them back to reality, my model is still going to fit really well, but not be quite so crazy, not fit so much to noise in the data. We're going to combat the overfitting and multicollinearity by purposely and in a systematic manner making our model's wonky coefficients smaller. That's really what regularization is. Regularization reduces the extremeness of model parameters. It's a method of penalizing the model's complexity and forcing our coefficients, in the linear regression specifically, to be closer to zero, to be less extreme. Okay. Now we get to go into a little bit of mathematical background. What I hope you get from this by the end of the day is I'm going to show you 3 different regularization techniques. One is called ridge regression, also known as L2 regularization. One's called lasso regression, also known as L1 regularization, and one's called elastic net regularization, also known as L1.5 regularization. And those numbers, 1 versus 2 versus 1.5, is literally the only thing about them that changes. It's a setting that gets set with those models that is going to cause them to reduce these coefficients in slightly different ways, but that at the end of the day, the differences between these 2 regularization techniques is really, from an implementation perspective, not that big. So we're gonna, now that I've introduced what regularization is, we're gonna take a couple of steps back and talk about, okay, how the heck does it squish down these coefficients? And that L1 versus L2 versus L1.5, those 3 numbers, has a big part to play in it. Okay. For those of you who maybe haven't taken a linear algebra course, the first thing we need to talk about is what a vector is. A vector is basically just a container of numbers, but in linear algebra, a vector is said to have 2 properties, a magnitude and a direction. A magnitude and a direction, right? If we take the items in a vector and we plot them on a graph, we would essentially treat them as a coordinate pair, where we'd go over 2 on the x-axis, up 3 on the y-axis, but instead of putting a point, instead of putting a dot, we'll draw an arrow from the origin to that point. So here's how we plot the vector 2, 3. It's an arrow from 0 pointing to spot 2, 3. That is the vector 2, 3. It's exactly the same thing as just putting a dot here, putting a point here, but in a linear algebra flavor. Okay? Well, we can see that this vector is pointing in a specific direction along in our coordinate plane, and that it has a magnitude. The magnitude is the length of this vector. So if you hear magnitude, just think length. Okay? So how can we calculate the length of this vector? Well, we could use something called the L2 norm. The L2 norm is our traditional distance calculation, which we can think about as if we used Pythagorean theorem and took the opposite and adjacent sides, the 2 straight sides, and we do a squared plus b squared equals c squared, right? To solve for c, we just take the square root. So we have the square root of a squared and b squared. Well, what are a and b? A and b are the lengths of the red and green side, respectively. So the length of the red side is 2, and the length of the green side is 3. And those are also the same numbers that are in the vector in the first place. So this is a, this is b. We just stick them in for a and b, and that is the equation for the length of a vector with 2 sides. Just take the numbers, put them directly into the Pythagorean theorem calculation. All right. So It's element 1 in the vector squared plus element 2 in the vector squared. Sum those up and then take the square root. This is called the norm of a vector. That's another word for a vector's length. And with NumPy, the calculation is pretty easy. 2 squared plus 3 squared is 4 plus 9, which is 13. The square root of 13 is about 3.6. Okay? That is the length of this blue line. That is the length of that vector. Pretty simple, right? Well, what if we had a 3-dimensional vector where we added a third number to it? Well, now if we were to plot this, we would now need to plot it in 3-dimensional space, which gets a little wonky, but we can still do it. But then how does the distance calculation change? Well, it doesn't change very much. We just add another term under the square root. So we have the first item squared plus the second item squared plus the third item squared. Sum those all up and then take the square root of the whole thing. I don't know why it says list item, list item. Okay, so 2 squared plus 3 squared plus 5 squared is 25 plus 9 plus 4, which is 38. 4 plus 9 is 13 plus 25. Yeah, it's 38. The square root of 38 is, drum roll. That's not right. Wait for it, drum roll. .16. That's the square root of 38, right? So that is distance and the calculation of distance as you have always known it. That is the straight line distance between 2 points. In this case, the origin and wherever the vector ends. Okay, that is how you've always calculated distance your whole life. You maybe haven't broken it down to use Pythagorean theorem, but it's the distance it travels along the x dimension squared plus the distance it travels in the y dimension squared. Add those together, take the square root. That solves for the hypotenuse, the length of the hypotenuse of that right triangle. Okay, that is the L2 norm. The L2 norm, and these should not be here. This should be above. Sorry, some things got out of order here, but I already put it back in. All right. So did you know that that's not the only way to calculate distance? There's another way to calculate distance that is called the L1 norm, also sometimes called the taxi cab distance, right? So the green line here, that is the L2 norm, right? We call that the straight line distance, or, you know, if this is a map of a city, these are the city blocks, right? And the gray lines are the roads. We would say that the distance on the green line is, quote unquote, as a crow flies, right? Now, a crow can fly up and over the buildings, fly in a straight line. That is the as a crow flies straight line distance. That's the L2 norm, okay? The L1 norm is sometimes called the taxi cab norm because it's the distance a taxi cab would need to drive in order to get from A to B, okay? Now here's a little bit of a tricky question. Which of the following 3 lines is longer? Red or blue or yellow? Red or blue or yellow? Okay. Well, this is actually a trick question. All 3 of those lines are the same length. It doesn't matter how many turns you take. If you're going the same horizontal distance and then the same vertical distance, taking right angle turns, if you measure the red line, the blue line, the yellow line, they're all the same length. Okay. So that is the L1 norm. Instead of calculating this diagonal line, we just add up the distance traveled in the horizontal direction and the distance traveled in the vertical direction. The taxi cab norm, it's as a taxi cab would drive. So essentially what we do is we just take the absolute value of the items in the elements in the vector and then add them up. So absolute value of 2 is 2, absolute value of 3 is 3, add them up and we get 5. That's the L1 norm of this vector. It's a measure of distance, but it's a different distance measure than maybe you're accustomed to. Okay? Same thing if we had a 3-dimensional vector. Just, again, add another term. We just take the absolute value, then add them all together, and we get 10. Right? So that is the taxi cab norm. That is the L1 norm. It is a very simple calculation. Take the absolute value of each of the items, then sum them up. We get 5 and 10. wow, there's more than one distance calculation. Maybe you knew that, maybe you didn't, right? Well, there's actually infinitely many distance calculations, okay? And we can generalize the equation for distance into this equation here. We call this the LP norm. It's not the L1 norm, it's not the L2 norm, it's LP, and P is a parameter which we can indicate. Okay, let me zoom in here. What do we get here if we plug in 1 for P? Well, then I take the absolute value raised to the 1 power. That doesn't change anything. Then all of that raised to the 1 over 1 power. That doesn't change anything. So if P is 1, then this becomes the L1 norm. But what if P is 2? Well, then I'm going to square each of these inner values, and I'm going to take it to the 1/2 root, which is the same as taking the square root, right? So if P is 2, then this is the L2 norm. This is the as a crow flies distance. One moment here. Need to take a pause for a brief second. Okay, sorry about that. My daughter came in for a moment. Had to tell me something. Okay, so we've got the L1 norm, the L2 norm, and we have a generalized equation that can calculate both of them. Well, we can really change P here to whatever we want. And as we do so, we'll get a different distance measure. Okay. And each of those different distance measures leads to these different shapes. If P equals 0, we get this wonky cross. All of the points will fall exactly on the axes. Actually, before I talk about this, let's focus on this guy right here, this diamond. This is the L1 norm. What is this diamond really showing us? Okay. Well, let me show you something here. Pick any coordinate pair whose values add up to 6. Okay. So what I'm essentially saying is I'm going to fix the length of this vector as being 6. Meaning the two items, the two elements inside of this two-dimensional vector have to add up to 6. So I might get 1 and 5, right? I might get 5 and 1. I might get 3 and 3. I might get, oh, I'm sorry, their absolute values have to add up to 6. Their absolute values. So I could get -3 and -3, because the absolute value of -3 is 3, absolute value of -3 is 3, add them together, I get 6, right? I could have -4 and 2. I could have 2, -4. I could have 3 and -3, right? Just the absolute value of the first and the second number added together have to be 6. Can you see the shape that is starting to be formed here? Okay. Can you see that all of these fall on the outside of this diamond? Right. So this diamond represents the boundaries of all the vectors that could be made using, if I fixed the length of the vector at 6 and my distance measure was the L1 norm. Okay? So the border of this diamond represents the longest vectors, or the most extreme inner vector values that would give me a L1 norm of 6, distance of 6. That's why when P is equal to 1, I get this diamond shape. Okay? If P was equal to 2, if I was using my regular distance measure, It'll be like if I took, my pencil, set its eraser here at 0, and then twisted it around in a circle. That straight line distance going in any direction would be the maximum length vector, right? So that circle shape, that area represents all, or the boundary of that circle, its outer edge, represents all the different vectors that I could make whose length would be fixed at 6, for example. Okay, so as you see these different shapes, which you'll often see when we're talking about regularization, when we're talking about these different norms, these shapes represent all the different vectors that could be made from a vector of fixed length. If we changed all the inner values to who knows what, right, but kept the length of the vector the same, that's the boundary. Okay? So what does this boundary represent? Well, if I take all of my model's coefficients, all my linear regression coefficients, right now back to linear regression, and I put them in a big old vector, in a big Python list, NumPy array, whatever you want to call it, but a linear algebra vector, that vector has a length that can be calculated using the L1, the L2, the L whatever norm. Okay? So here's my array of coefficients in a vector. There's 302 of them. Okay? This is the L2 norm of my current vector of coefficients, and this is the L1 norm. Okay? One of the ways that I can take the inner items inside of those vectors and make them smaller is to say, hey, this vector is too long. Its norm, it's the distance it reaches out into 302-dimensional space is too far. What if I forced this vector to be shorter? And if I forced this vector to be shorter, maybe if I penalized the weights, then the items inside of the vector would also be forced to be smaller in order to not make the vector too long, right? So really all that regularization is taking all of our model's weights, parameters, coefficients in the context of linear regression, put them in a big list, have a calculation that quantifies the length or the size, the quote-unquote magnitude of that vector, and then say, hey, that vector is too long. That vector of coefficients is too long. What if we made it shorter? How are we going to make it shorter? Well, let's fix its length and force the inner values to be smaller in order to correspond to that smaller length. Okay. Now here's maybe the weirdest set of visualizations from today. Oh, it looks like my focus has gone off. There we go. Okay. Over here we have our L1 norm. Okay. And remember, we have that diamond shape. The edge of this diamond represents the longest vectors I can make of a fixed length stretching in any direction. This is the L2 norm. And this over here, it's called the L1 plus L2 norm. This is actually the L equals 1.5 norm. And this funky shape, some say it looks like a net that's getting cast out into the water, maybe an elastic net. Okay, so you'll see it's somewhere in between the L1 norm and the L2 norm, and it's kind of this round yet pointy shape all at the same time. Okay, so L2 is the circle, L1 is the diamond, L1.5 is that weird yellow shape that's in between the two called elastic net. Okay. All of these, if I'm just changing the value of p in my distance calculation, puts a slightly different constraint on my vector of coefficients, my vector of model weights, and is forcing them to shrink down in a slightly different way. Okay. Well, what's going on with these ovals? These ovals represent our loss function, just like we saw with gradient descent. Or to not pull up our old notebook. Something like this, right? This was our loss function with gradient descent. It was kind of like two parabolas when we did simple linear regression. And then the circles on this flat part here is what we call the contour plot, right? We're seeing those same circles where the innermost section represents the minimum of the loss function and the outer rings represent being further away from the minimum of the loss function. Okay. Well, what I'm saying here is that if I allow my model to converge to the minimum of the loss function, that it's going to be overfit. So if I constrain the set of parameters using the L1 norm, that's going to force the model's coefficients to be a little bit smaller, and it's not going to be able to, the model's not going to be able to get all the way to the minimum of the loss function. It's going to be constrained a little bit. And so it gets constrained in slightly different ways if you use the L1 versus L2 versus elastic net L1.5 norm. But there's this trade-off that's happening. I'm trading off some of the model's bias. I'm making my model a little bit more biased to make it a little bit less high variance. So I'm making it so my model doesn't overfit as much, but as I do so, I need to be a little bit more, allow my model to be a little bit biased. It's this trade-off, right? You can't get one without the other, generally. Okay. So you'll hear people talk about ridge regression, lasso regression, and elastic net regression. These are all linear regression models that use quote-unquote regularization. And all that regularization is forcing our model's coefficients to be smaller according to one of these three constraints. The L1 norm is known as lasso regression. The L2 norm is known as ridge regression. And the L1.5 norm is known as elastic net regression. Okay? And there are some slightly different characteristics to how the coefficients get modified under each of those three. But at the end of the day, the only thing that I'm changing between L1, L2, and elastic net is I'm changing my value for P from 1 to 1.5 to 2. And if I wanted to, I could really use any value of P. As P goes to infinity, I get closer to this square. As P goes closer to 0, I kind of get this plus sign figure, right? We usually don't go less than 1, and we usually don't go greater than 2, somewhere in the middle there. But these three different regularization techniques is just the change of one number, from 1 to 1.5 to 2. And really, we're going to test them all against our model. Each of these three different kinds of regularization. Each of them is going to force our model's coefficients to be smaller. And in that way, it's going to make our model less wonky, less overfit. We're going to trade off some bias for variance. And if we do that correctly, right, instead of, where's my bias variance trade-off graph? Right? Right now, we have a model that is too high variance and it's pretty low bias. If I allow my model to be a little bit more biased, I'll be able to decrease the variance a lot and be able to get to a model that generalizes better, makes better predictions. We're too far over here on the right, and we want to come back into the middle, force our model's coefficients to be less crazy, be less extreme through regularization. Okay. Now, the actual calculation, we're not going to go over because it's a little bit involved, but essentially we penalize add a penalty to our loss function, our cost function, that does essentially just what you're seeing in these diagrams right here. Man, we've got a lot of stuff in today's notebook. These diagrams right here. We're going to be a little bit off from the minimum of the cost function, but in ways that's going to decrease overfitting and lead to a model that generalizes better. Okay. But there's one other thing we need to indicate. Well, what should I fix? What should the fixed length of this vector be? right? This boundary only exists if I fix that vector's length to a certain value. Well, the way that we're going to kind of control that or indicate that to our machine learning algorithm is by setting a parameter called the regularization strength. The regularization strength is a value that we pick before the model gets fit, and it is not learned in the training of the model. It's just we as the data scientists say, oh, I think the regularization strength should be 0.1. It should be 5. It should be 100. We're going to say what we think it should be before the model runs. Okay. Any setting that has to be provided to the model before it's fit gets a special name. It's called a hyperparameter. And we don't know what hyperparameter is going to be best. We don't know what regularization strength value is going to be best before we train the model. So we're going to try a bunch of them. And we're going to see which one works the best, which regularization strength leads to the model that gets pulled back to the middle of that sweet spot and generalizes well to unseen data. Okay. So let me show you here. I'm reloading the train and test data. I'm making MS subclass categorical. I'm doing the one-hot encoding, breaking back out into train and test, filling the null values. This is all things we've done before. I don't know why it's saying it should be subject to a license. I'm going to do a little bit of an extra step here. I'm going to standardize the data. And this is just going to help these models find the minimum of the cost function a little bit better. It essentially takes our cost functions, and instead of them being kind of lopsided like this, and actually we saw this kind of lopsidedness when we were talking about gradient descent, how one of our models' parabolas was like really steep and the other one's really flat. Well, they would have been about the same curve if we had scaled all of our data down, which is what we're doing here. You can look up this scale function from scikit-learn if you want. It's essentially turning all of our data into z-scores. So all the patterns in the data are still there. It's just changing them so they have about the same scale. Instead of something being measured in tens of thousands, another one being measured from 1 to 10, it's putting them all in the same ballpark. And this really just helps gradient descent find the minimum. It kind of rounds out our loss function. Whoop. So instead of our loss function being lopsided, our loss function will be a little bit more circular. Helps it get to the bottom faster. It has a couple of other benefits as well, but that's mainly why we're doing this, is because I know from working on this earlier that if we don't do this, then some of our models will yell at us and say, hey, we haven't found the true minimum. Maybe you should scale the data. So I'm scaling the data so that our models don't yell at us. Okay, but because I need to try out all these different regularization strengths, I want to use cross-validation to make sure that I can compare those different experiments effectively. So I've got a function here. It's going to do the cross-validation with 5-fold cross-validation, give me the root mean squared error. Sorry, it's going to give me the mean squared error, which then I'm going to take the square root of, and I'm going to then return that value. So it's going to try out a whole bunch of different values that I provide for regularization strength. And it's going to spit back out to me the model's root mean squared error for each of those regularization strength values. Now, typically we don't use values this big for the regularization strength. We're using these big values because our y variable is really big. The value of the homes is in the hundreds of thousands. So these regularization strengths are larger than we would typically see. We also have lots of coefficients. So these regularization strength values are also bigger than you'll typically see. But I can change these values to whatever I want. They're just different experiments that I'm running. Say, what if my regularization strength is 500? How well does my model do? What if it's 700? How well does my model do? And then I'm just going to pick the model that does the best. Pick the regularization strength value that does the best. Okay. So I'm going to run these different experiments. I'm going to put the results in a data frame, and then I'm going to pick the best one. Oh, I got to run these code cells, make sure that I'm running them. So I'm running a ridge regression every single time here. I loaded the ridge regression at the very top of my notebook. And now I'm sorting the model's performance. Looks like a alpha value of 500 is giving me a root mean squared error around 31,000. And this is, I would expect similar performance on the test data, maybe a little bit worse than I'm seeing here on the cross-validation. Okay. That is ridge regression. Ridge regression is using the L2 norm. It's making my model coefficients be smaller. In fact, let me show you. Well, I don't know if I can show you, because my ridge model is stuck here inside of this list comprehension. I'll show you a little bit later on. So here's ridge regression. The best results we get are around 31,000. Lasso regression, L1 norm. Best results we get around 31.3. So maybe off by 300 or so. Quite a different alpha value. Here's elastic net. P equals 1.5, just a different way of constraining the magnitude of a vector. That's all it is. And the alpha here is around 2, right? So much smaller alpha. It's better with elastic net. Some of these are just due to the different specifications of how that penalty is applied to the cost function. But we can experiment with these different alpha values. Okay, and it looks like 31.34, 31.345. Looks like ridge regression is doing the best for us. Okay, so let's continue to use ridge regression. And let's compare, what do our coefficients look like after ridge regression versus what do our coefficients look like without any regularization at all. So just to prove and make it extra clear that like the two models I'm about to show you are working with exactly the same data, I'm loading it all fresh and I'm cleaning it all again. Again, that's not something I typically do. I just want to really prove to you that these models are facing exactly the same data. We're going to have a linear regression model and a ridge regression with an alpha of 500, that regularization strength. And then I'm going to plot on the same graph the coefficients of the linear regression versus the coefficients of the ridge regression. Okay? We've seen this blue graph before. We saw it up above, right? And the orange line is the ridge regression. See how they're not really extreme coefficients in here? It almost looks like a straight line. I don't know how to make it that much bigger, right? Our coefficients are not being allowed to go wonky because we're constraining the length of that vector of coefficients. And it's not allowing any coefficient to have a value of negative 500,000 because that would make the vector too long, right? And this is leading to much better predictions. We've come down, we have a slightly more biased, but way less variance model. This has been a good trade-off for us. This model is going to actually make much better predictions than an out-of-the-box vanilla linear regression due to the number of x variables we have, tendency for overfitting, and multi-collinearity between our x variables. Okay. So if we look at just the ridge regression coefficients, they're all in the same ballpark. We have one that's a little bit extreme, but maybe it should be. This might be overall quality, right? The quality of the home increases the value by around 10,000 or so. It's a far cry from the 40,000 or whatever we saw when we did the simple or small multiple linear regression model. Okay. We also have a lot of coefficients here that are pretty close to 0. We have some coefficients here that are maybe not doing anything. Maybe nobody cares in Ames, Iowa if your masonry is brick versus not. I don't know, right? Like maybe there's just something that's really not moving the needle in terms of the price of the home. And maybe we could exclude some of those variables, but we're not going to take the time to go and comb those out today. We're just going to leave our kitchen sink model as it is because we're still going to get good predictions with the kitchen sink model. Okay. So that is regularization. Now, if I did this alone, we would beat our predictions from last time. The regularized model, in fact, is going to do quite a lot better than the regular model, but I want to make one more improvement to our modeling that we haven't ever done. And I want to control for the skewness of some of our variables. So this is a totally new topic. And we're going to do this through something called log normalizing. Okay? If I remind you, the sale price column looks like this. Right? And because it kind of has this right skew, we have some outliers here. And we don't like outliers in linear regression. They pull on the linear regression line more than other values do because we're looking at the sum of squared residuals, right? The residual of this one property, or however many properties are out here, looks like multiple properties, is going to be so big, and then when we square it, it's going to be giant, and it's going to have an outsized influence on the placement of our line of best fit. If I take the natural log, well, I'm going to add 1 to the value, and then I'm going to take the log, because the logarithm graph for values that are close to 0, it goes to like negative infinity. And so in order to avoid like some of our values getting pulled to really negative numbers, we're going to add 1 to them first and then take the log, and that's going to kind of avoid some of our numbers getting like sucked down to 10,000 kilometers below the sea or whatever by the shape of this graph. So we're going to add 1 to each of our sale prices. And this really isn't a problem with the sale price value. We don't have many sale prices close to 0. It could be a problem with some of our other skewed variables. So not really necessary to add the 1 here, but we're going to log normalize by adding 1 every time, just as a convention. Okay, add 1 to each of the sale price values, then take the logarithm, and what this does is it kind of makes the distribution more symmetrical. We say this log normalizes. Now it's not exactly normal, it's still a little bit skewed, but it's much less skewed than it was before, and this outlier has kind of become more normal, come back into its regular range, and our model is going to be able to attain a much better fit here. Now this is one example of not exactly a polynomial fit, but it's a nonlinear fit. And we actually, in our data set, have quite a few skewed variables. And so it's most important that I do this to the y variable, but there's some other x variables that I can do this to as well. The one downside is that my root mean squared error goes from being in dollar terms to being the log of dollars, which is not something you would choose, will not be your first choice of error metric. But what it does is it makes it so that my error metric, instead of being measured in terms of dollars, is measured in percentage terms, which is kind of weird, but oddly enough, still pretty understandable, right? So if I calculate my root mean squared error of the log of sale price, and it gives me back 0.14, that means my predictions are off by about 14% on average. Okay? And in fact, if I use root mean squared error and I use a log normalized y variable column, that is exactly the same metric that Kaggle is using on its leaderboard. Another reason why I bring this up. And that's why Kaggle has chosen that, because they know it's a best practice. They know you're probably going to be doing that anyway. And so if I remind you how good of a model we had last time, house prices, leaderboard, and I think I've made a new submission since then. So my score here is actually going to be a lot better than we saw last time. Okay, if you have 0.12, that means you're predicting home prices within about 12% of their true value. We're off by 12.4%. Okay. I think we were actually off by like 14.5% last time. This is going to be our model's performance at the end of our discussion today. I just made a test submission to make sure that I hadn't done something terribly wrong. Okay, so this is a best practice when working with a skewed y variable. Changes our error metric from being in terms of dollars to being in terms of percentage of the home's price, which at the end of the day is still somewhat interpretable. So it's nice. Okay, so let's make that transformation. We're overriding the old sale price with the log of the sale price. Okay. Now I'm going to put everything into the same data set again like we did before. And now that it's in this same data set, I'm going to check for skewness across all of my variables. And I'm using this SciPy skew function, and if that function returns to me value greater than 0.75, then I'm saying, all right, that's a strong enough skew that I'm going to be worried about it. A strong enough skew that I'm going to try and address it. And it turns out that all of these columns have a strong enough skew for us to do something about it. For reasons that are similar to the sale price column, let's look at plt.scatter between the, let's see, actually, let's look at a histogram, sorry. plt.hist of train lot area. Okay. And let's increase the bin size, or the number of bins rather. And it looks kind of skewed, right? We've got this big spike at the left and moving to the right. Now, we have like some weird property that is really giant out here that's kind of squishing all this. I wish I could turn that off. Oh, I just meant to set that to 40. Oh, maybe 240 is not bad, actually. These are really small bin size, but now you can see the shape a little bit, how it has that long tail off to the right, and it's bounded at 0. So it has that skewness to it. If I, is it log 1p? What is the function name? NP, yeah, log 1p. If I take the log of it, then it normalizes. Okay, this is going to help our model fit much better, much better. So I'm going to log transform all of these guys that I just saved in skew columns by calculating their skew, and if it was above a threshold, threw them in here. And that's the last thing we're going to do to this data set. So between regularizing the data and controlling for skewness, one-hot encoding, filling null values with either the mode or the mean, based on if it's a categorical or numeric column. That's really all we're doing to this data set. Okay, so let me show you again. And I think I started over here again. Okay, so that's just a graph. This is going to take all of the columns that we identified as skewed and log normalize them. Okay. Then we'll do our one-hot encoding. Then we'll break it back out into train and test. Then we'll fill our null values. And then we'll do our ridge regression test again, right? Because maybe the alpha value is different now that I have controlled for this skewness in some way. Right? Typically, after I take the log of values, their scale drops by quite a lot. So I might need a different alpha value here, and I've already tested this, so I know what it is actually. Okay. If I plot this, looks like an alpha value of around 10 gives me the lowest root mean squared error. Okay. Which is why I chose these values here. So I'd already played around with this. This is a little bit of a canned demonstration, but this is all things we've seen before. Okay. And now I'm ready to generate my final predictions. Okay. It says this is my best performing model. I'm off by about 12.7% on average. That's not too bad. That's much better than the 14.5% we were off before. Right? So this is by far the best model we have created together in our machine learning workshop live streams. So let's get one final fit. We're going to train on the entire data set at once, make our predictions on X test. Now the one wrinkle here is my predictions are going to be the log of sale price. Kaggle doesn't want the log of sale price submitted. They want actual sale prices. So I have to reverse the logarithm by using an exponential function to undo the logarithm. So I'm like unlog transforming these to get them back in a format that Kaggle will like. So this is undoing undo the log transformation before we can submit to Kaggle to get the y variable back in dollar terms. And then I can generate my submission data frame, export it to a CSV, download it from Google Colab, and I can go and make my submission to Kaggle, which I don't think I'm going to get any different results here. I've kind of already spilled the beans. Unless I've made some error. I could have run a code cell out of order or something like that. 12.446. So the same as we had before. Let's see where we fall on the leaderboard. Reminder, there's about 4,600 participants in this competition, and we are now positioned 4,421. Mm-hmm. 421 divided by 4,600. We're in like the 91st percentile, somewhere around there. We're in the top 10% of models by doing these few things that we've done. Final review. What have we done to this linear regression model? We log transformed the y variable. We identified skewed columns. We log transformed all of the skewed columns. We one-hot encoded the categorical variables. We filled the null values with the mean or the mode. And we fit a ridge regression model with a good, the optimal regularization strength, so that our model didn't go so wonky. So we decreased over the amount of overfitting. And that's really all that we've done, right? We could have fit this whole model and done all this stuff in 12 to 16 lines of code if we knew from the get-go that that's exactly what we should have been doing, right? It's taken us so much experimentation and so much data exploration to learn that that's exactly what we should do. And a lot of times that's the result in data science. You do a lot of work to get the right 15 lines of code. You write thousands of lines of code to narrow down the final 15 lines of code that are going to determine the very best modeling, the very best data cleaning and treatment. So a lot of demonstration code here in this notebook today, which is why we didn't type a lot of it in from scratch. But we're doing pretty well. We've made pretty good predictions with our ridge regression model, and in fact, I think in order to get a much better model, we could do a couple of feature engineering tricks, which we're not going to take the time to do here. But really, besides that, in order to get better predictions, we would have to go to a totally different category of model, a non-linear regression-based model like an XGBoost or a random forest. And if we did that, we could maybe increase our model's performance another % or so, right? But I want you to notice that, let's see, the people around us have their performance is crawling upwards little by little by little by little. Okay. If you had 0.11% error, like 11% error, you'd be like in the top 200. These guys with very tiny errors, they're all kind of copying one smart person's really good submission, or they're just cheating like this person is. They downloaded the data set from somewhere else and submitted all the exact right answers. So don't expect yourself to be up here. That's not reality. That's people just copying somebody else's work. Whereas any of us, through learning about ridge regression, learning about log transformation, learning about filling null values, learning about one-hot encoding, could have gotten in this ballpark here today. Okay, we're doing pretty good. And with this, we're gonna kind of let this be our final discussion of linear regression and linear models. We now have regularized linear models, which is about as good of a predictive model as you can get with linear regression. We actually won't have a machine learning workshop next week. I will be out of town all week next week. I'll send an email reminder about this. Yeah, this is the last touching on linear regression we're going to do, I feel like it's time we moved on to some other cooler stuff. And we've had a good introduction to predictive modeling and some statistics concepts through this vehicle of this project. But I think it's time for some fresh material. So, alrighty. Thanks for your time. Thanks for being here. Even those of you I know who are catching this through the recording because you can't be here live, thank you for taking the time to read this. I appreciate any likes and comments on the video to feed the algorithm. And we will be in touch. Have a great evening, everyone.